Hi everyone, my name is Bliek and I'm an assistant professor in Eindhoven University of Technology. And I will be presenting our work on black box mixed variable optimization using a surrogate model that satisfies integer constraints. This work was done together with Guijt, Sicco, Verwer and Mathijs de Weerdt. So I will start this presentation by very quickly going through what is a surrogate model, how is it used for expensive black box optimization. I will assume that most people in the workshop, which is the SAEOpt workshop, already know about this, so I will not spend too much time on that part. I will then dive into the mixed variable setting, where mixed variable means continuous and discrete in terms of which variables we have in our problem. And then I will explain the proposed algorithm and finish with the conclusion. So in expensive black box optimization, we have a certain objective function, but we have a few assumptions. For one, it is of course black box, so we do not have any assumptions on linearity, convexity, we don't have a formula, we cannot calculate derivatives. But other than that, our function is also noisy and expensive. So when evaluating this objective function, we have to spend some resource, usually computational resources, to get the result y, and due to randomness there can be noise when evaluating the objective function. Because of the expensiveness, we only assume that we have a limited budget of samples available. Now, these assumptions, they appear quite a lot in different applications. For example, in automatic algorithm configuration, where we want to tune the hyperparameters of some algorithm, and to see how good the hyperparameters are tuned, we have to run the algorithm, which takes time. The same holds for automated machine learning, where we have to wait until the machine learning algorithm is finished training before we can see how well the hyperparameters are chosen. And automated machine learning is an interesting one because there it is quite natural to see how mixed variable cases pop up. If you have, for example, a deep neural network and you want to tune both the learning rate of the neural network and the number of layers or number of neurons, then you have an example of a mixed variable case where you want to tune both continuous and integer variables. There are also a lot of different simulations where that have an expansive objective function, because when you want to tune the parameters of your simulation, you have to wait for the simulation to end before seeing the results. Surrogate models are the best type of method that can deal with the expansive setting of an expansive objective function. And they all work in similar ways. They evaluate the objective at the current candidate solution, starting from maybe an initial guess or some default value for the parameters. Then they approximate the objective with a surrogate model, and this is purely a machine learning step. And then they use this surrogate model to choose a new candidate solution. This can be done with evolutionary algorithms, as is the main topic of the SAEOpt workshop. However, in this work we are not limited to the use of evolutionary algorithms, but we mainly look at continuous optimization solvers in this work. And then after repeating for several iterations, over time the approximation of the surrogate model becomes more and more accurate, and as a result it will propose better and better candidate solutions that solve the optimization problem. Now, there are different settings where surrogate-based optimization methods are applied. The most famous one is the continuous setting. So there is a large tradition, a large history of surrogate models, mainly in the Bayesian optimization framework, with the use of Gaussian processes as surrogate models, as you see in the picture, as an example. And there's a lot of literature available, and we know quite a lot about this setting. For the discrete case, it's a bit more complicated. We have several methods that can deal with this. For example, when you use a discrete surrogate model, such as a random forest or a decision tree, then you can naturally deal with the discrete variables, although other methods to deal with discrete variables exist. For the mixed case, the literature on this topic is very limited. There are several methods that can deal with this, but what the best way is to make use of the strengths of both the continuous and the discrete knowledge that we have of surrogate modeling and of the different problems. This still remains unclear, and the literature on this topic is very sparse. Now, you would think that you could just combine the use of, for example, a continuous surrogate model and a discrete surrogate model, but this combination is rather tricky. It's not as straightforward how to do this. So in our work, we develop a new technique to really focus on the mixed case by making use of the strengths of continuous and discrete optimization problems. Our approach is called MVRSM, which stands for Mixed Variable ReLU-based Surrogate Model, where ReLU stands for Rectified Linear Unit, and this is a common basis function used in machine learning, especially in deep learning. And as a result of using this type of basis function, our model becomes piecewise linear, as you see in the figure where we have applied our model to a very simple problem, a traveling salesman problem with 4 nodes. But this is just for visualization, where you can see the piecewise linearity of the surrogate model that we use. So this does mean that our surrogate model is continuous. Even though we look at a case where there are discrete variables present, we do not limit our surrogate model in that aspect. However, because the model is piecewise linear, we can choose more or less what it looks like, and we design it in such a way that when you arrive at the local minimum of the surrogate model, which can be done using straightforward continuous optimization techniques, such as gradient descent, at this local minimum, the variables that are supposed to be discrete or integers take on integer values. And this is the main selling point of this method. Just to elaborate on how this works exactly, as you saw in the three-dimensional model, there are some areas where the model switches from one linear region to the next. Let's call these boundary functions. And as you see in this model, if you would follow a gradient descent algorithm on the model, you would end up in a point where this variable is an integer. But it's not straightforward how to choose these boundary functions. We can choose them, and then the model will take on different shapes depending on the data that it receives from the expensive objective, but we can limit these boundary functions. And we do that as follows. Let's say that these are the different boundary functions, and between these boundary functions, the model is linear. So this results in a piecewise linear model. And let's look at a very simple case where we have only one discrete and one continuous variable. xc is a continuous variable, xd is a discrete variable. Now what we do is we place these boundary functions exactly in areas where this discrete variable takes on an integer value within the search space. Then the other boundary functions, they will cross these other boundary functions in areas where the discrete variable takes on integer values. Why is this important? Well, as you see in the 3D model, which does not correspond exactly to the other figure, but has the same idea, where these boundary functions cross, that is exactly where the model has a possible local optimum. In fact, all the local optima of such a piecewise linear model are located in points where these boundary functions cross. So we have 4 possible local optima in this case, and by the way we designed these boundary functions, we chose these boundary functions, they can only be located in points where the discrete variable takes on integer values. Now there is one thing we need to take care of here, and that is these let's call them these diagonal boundary functions over here. They are chosen parallel to each other. If they were not chosen parallel to each other, they would cross in some other part of the search space, and then the model would have a potential local optimum in a point where this discrete variable was not integer. So we have to take great care on how to design all the boundaries of the piecewise linear model, and we make use of this. And we have theory available in our paper, including theory of what happens in higher dimensions than 2 dimensions, because then everything becomes more complicated. But we provide a proof that no matter how the model is shaped according to the expansive objective function and the data it receives, it will always have this property that when we find the minimum of the model, the discrete variables take on integer values. Let's go on to the results. So how does this method compare to other methods? We first made a comparison with other surrogate optimization methods on synthetic benchmarks, and we tried several synthetic benchmarks. Our method is in blue, MVRSM over here, and other methods that we compared with are random search, SMAC, HyperOpt, and Bayesian optimization with Gaussian processes as 3 very standard surrogate modeling algorithms that are still used in many different problems. Random search is just included as a baseline. Now what you see on the horizontal axis are the iterations of the algorithm, and on the vertical axis you see the objective, which is to be minimized. And over time it goes down for all methods. However, for MVRSM, which is our proposed method, it goes down after enough iterations. It will go down faster than for the other methods. We also plot the computational time that every algorithm uses. So this is not the computation time of the expansive objective, as these are just synthetic benchmarks, but of the algorithms. And we see that our method has another interesting property that we purposefully built in, that it does not become slower over time. There is no slowdown of the method. It has a fixed computation time per iteration. While the other methods, they have a varying and usually increasing computation time. So this makes our method also more useful in the case that you want a faster method, or you want a method that you know in advance how long it will take for every iteration. And you can play with this. We can change the number of basis functions to make it slower but more accurate, or the other way around. But we use the same number throughout all these experiments. This benchmark, by the way, is a synthetic benchmark taken from a library of mixed integer problems, and it contains 20 integer and 20 continuous parameters. And we see similar results on a synthetic benchmark from a related paper, which is the MIVABO algorithm. MIVABO is an algorithm that also takes place in the mixed variable domain. And we see that we have similar results here, where our method outperforms the other methods and has a fixed computation time per iteration. And this was quite a large-scale example with over 200 variables in total. And we tried different combinations of more integer variables or more continuous variables. And we saw that especially in the large-scale problems like this one, our method outperforms the other methods. Also, the Bayesian optimization methods, as you can see, they increase in computation time, and they become too slow, especially for more iterations or for higher dimensions. So we did not include them in all experiments. Now on to the real-life benchmarks. We have included 2 of them, one from engineering and one from computer science. This benchmark is called Electrostatic Precipitator, and it is concerned with designing a gas filter to filter pollutive particles. It has almost 50 categorical variables, so we tested this even though our method was designed more for integer variables, and we included 5 continuous variables that influence these categories, so there is also a clear interaction between the variables. We do not exploit the exact interaction, but we make sure that there is an interaction. In this case, we see that there are several methods that perform very well. SMAC, HyperOpt, and MVRSM all achieve statistically the same results on this benchmark problem, while MVRSM has a fixed computation time per iteration, although HyperOpt is quite a fast method as well. The other benchmark contains more variables, again over 100, and is concerned with tuning the hyperparameters of an XGBoost machine learning model and the pre-processing step. And in this case, there were also not only categorical but also conditional variables. And these variables, they only exist when other variables take on certain values. Now, SMAC and HyperOpt, they were designed for this type of method, and they perform indeed very well. But MVRSM still gives statistically similar results, even though it is not designed for these conditional variables, all while maintaining a fixed computation time per iteration. In conclusion, my take-home message for you is that piecewise linear models, although they are quite simple, they work very well for a mix of continuous and discrete variables. And this is due to our guarantee that in the local optima of our MVRSM surrogate model, it satisfies the integer constraints. This means we do not need to do any discrete optimization, just continuous optimization, which is very fast, is sufficient. And because of this, it's faster and more accurate than the state of the art for several synthetic benchmarks that we tried. And on real-life benchmarks that are a bit more complex, we achieve competitive performance with statistically similar results as other surrogate modeling algorithms. In the future, we plan to make this method be able to deal with constraints in the search space, as right now this is not there. And we plan to combine it with evolutionary algorithms, especially the ones that can deal with a mix of continuous and discrete variables, or just continuous variables, as our surrogate model takes care of the discrete part. And we plan to include more real-life benchmarks and investigate why there is a difference in performance for our method between the synthetic and the real-life benchmarks. So we plan to investigate this to see if we can find more information and understand this part better. Thank you very much for your attention. If you have any questions, my email is on this last slide. And thank you again.